Well, if we have a closer look, the features that are concerned with running are time measurements. So the lower values are better here in those disciplines. And for all the other features that are concerned with throwing and jumping, the higher the values are, the better. So we have somehow the problem that we compare apples with oranges here. In order to get the features somehow comparable, we have to think about something. So first of all, here you see the results of the best and the worst participants. So the gold medal winner was Jackie Joyner Kersey from the US. You see her measures here, and the worst was some Miss Launa. I don't know exactly. PNG, whatever that is. I don't know, people, but whatever. Sorry for that. That is not meant to be somehow with disrespect, but anyway, this is the measure of Miss Launa. So yeah, we have the problem that here with hurdles and running here and here, the lower the better, and all the others the higher the better. So how can we do that? Well, we can use negative time measurements. Yeah, for the time measurements, hurdles, 200 meter, 800 meter, we take the negative values. So again, then the higher the values, the better are the values. So we have all features in the same directions. The higher the values, the better the values. Yeah? So that is a small trick to make all the features somehow comparable, at least in the same direction. Yeah, we can have a look at the scatter plot matrix here, which you probably know. So we just compute all the pairwise, so we plot all the pairwise projections. We see some kind of correlations here, meaning that it might be maybe a good idea to use PCA. But on the other hand, I mean, the scatter plot matrices show you a little bit about the pairwise distances, but of course they don't reveal anything about higher or more complex correlations or more complex relationships between features. So be a little bit careful with scatterplot matrices. They show you a little bit of the relationships, but only pairwise. And there's no thing that tells you that two or more features depend together on each other, but are pairwise uncorrelated. That may happen, of course. But anyway, there seems to be some correlation, especially with hurdles and high jump and stuff like that. So let's see if we can get something with PCA. So if we perform PCA on this data set, we have the problem that they have different scales. So we carry them, the PCA out on the correlation matrix, which is equivalent to the correlation matrix if the features would be normalized. Anyway, so the result of PCA will be, of course, the scores, first of all, that are the principal components that are d-dimensional vectors, d-dimensional vectors, which gives us actually together the loadings, the loadings, the PCs are actually defined by the loadings and the original features, obviously. So we need the loadings for the PCs, then we get the PCs, and we get the standard deviation or the variance of these scores, which are the eigenvectors lambda 1 to lambda d. So since we have 7 features, we will get 7 loading vectors for 7 PC scores, 7 principal components with 7 eigenvalues. Sorry, the PCs are the eigenvalues actually. So now to the question, what kind of K should we use? Well, we could look at how many principal components explain what kind of proportion of the total variance. Well, the total variance of the D PC scores is equal to the total variance of the original features. So we have the sum of all the eigenvalues, the sum should go not to P but to D, is equal to the sum of the original variances of the original features. So S1 is the variance of the original feature, S2 is the variance of the original feature, X2, and so on and so on. And the squared is it's the total variance. So sorry, standard deviation, so squared is the variance. So the sum of all the eigenvalues give you the total sum of the variance. Yeah. So the proportion explained of explained variance of the jth of one specific principal component is the corresponding eigenvalue divided by the total sum that we have here. Yeah. So the first k principal components can be or account for the particular proportion, which can be computed by the sum of the corresponding k eigenvalues divided by the total sum. Yeah? And that gives us a kind of hint whether or not it makes sense to look at k, or what is a good k actually to cut off. And there are two simple rules of thumb for choosing k, the number of principal components that are enough. The first one is that we just look at how many percent of the total variation is explained by k components. So if we retain if k components, explain already roughly 80 to 90% of the total variance, by this formula here, then that is enough typically. So we typically choose as first rule of thumb the k components that already explain 80 to 90% of the total variance. That is typically enough. If this is not too clear, we get almost D, then we can use also a so-called scree plot. So we plot the component variances versus the component number and look for an elbow here in that plot, which would be here. So this is actually the figure for the heptathon data set. We have 7 principal components. We have the corresponding lambdas, the corresponding eigenvalues, which are plotted here as a bar, or as the height of the bar. And we see that the first principal component already explains more than 60% of the data, and then there is a clear decrease, and then there is a plateau. So there's a kind of elbow in this plot here. So all the components after this elbow are neglectable in that case, because we don't lose too many information anymore if we just keep them. So for our data set, actually the heptathon data set, since this is the plot that we get, it seems that we can really just take the first one, even though it's less than 80%. But there's some kind of clear elbow here. So let's hope for the best and just keep the first one here. So the first principal component actually explains, in the heptathon data set, actually explains 63 point something of the variation of the heptathon data set. And the loadings of the first PCs are something, which is nice to have, but anyway. So the dimensionality reduction is now that we project all the 7 features onto the first PC. And now let's have a look at the scores of the first PC and compare them with the official scores used to rank the athletes. Well, how to compare them? Well, we can plot the scores, the official scores. That is the sum of all the scores from all the 7 disciplines. For each discipline there, the particular measure gives a particular number of points, and the points are just summed up, and those are the official points, the total sum of the points. You see Jackie Joyner Kersee clearly had more than 7,500 points here, and the second one from Eastern Germany here had less than 7,000. So that is the official score on the x-axis, and on the y-axis we have the ranking according to the first principal component. And in the best case, of course, everything would be on a kind of line here, which is not perfectly the case, but at least you have, the 3 gold medalists at least are in the same order on the first principal component as on the second principal component. There are some misunderstandings or misconcepts, like the lady from Bulgaria here, for example, and the lady again from Eastern Germany. So in this case, Schulz would be better according to the official score. Dimitrova would be better when we just look at the first principal component. Yeah, but okay, so we make some errors, obviously, which makes sense because we just have 60-something% of the original spread, but at least overall, the overall picture is quite good. And the good news, especially for the medalists, is that each medalist would be the same as before. Yeah? So it's just to show you that we don't lose too much information, obviously, because we still can compare the individual athletes and get more or less the same ranking. Not the same actually, but more or less the same ranking. In most of the cases we get the same ranking. Yeah? And that's good actually. Okay, to sum up or to round that up, a short discussion. Yeah? Advantage is that, of course, PCA considers arbitrary correlations, at least linear correlations between features, so can be negative, positive, whatever. And the selected subspace that we get from principal component is optimal with respect to the total loss of variance. Yeah? At least if this is the assumption that we make, that is perfect. The disadvantage is that the assumption that the components with high variance are useful to discover the desired patterns need to be fulfilled. Well, first of all, this assumption is not a disadvantage, but we have to be clear if this assumption does not hold in our data set, which is some very often hard to prove or hard to check, then PCA doesn't make sense. Yeah? And well, of course, you can be a little bit picky and say, well, we only have linear correlations. What about nonlinear correlations? I already mentioned that there is a workaround called kernel PCA, and we will have a look at kernel PCA later when we talk about kernel PCA, surprisingly.